Morning, everybody. Do you hear me? Oh, great. Let's talk a bit about the circular motion because I want you to understand why is it important, the moment of inertia. So we've talked about it. Circular motion is nothing else, just you have a body, let's say A, that move around the circle. So this is a one-dimensional motion since this is the origin, this is the theta equals 0. We have only theta t, one-dimensional function that describes fully the motion. From the theta t, you can calculate the omega t, the angular, so this is angular displacement, this is angular velocity. You can get it by derivating it, and with another derivation, you can get the angular acceleration. These are the formulas you should know. So not only how to calculate the angular velocity from the angular displacement or angular acceleration from angular velocity, we have also the period of time, the time moving from one position to the same position, this is the period of time, and the frequency, which is 1 over t, the period of time. By historical reason, we don't use the 1 over s, but the hertz to describe it. So this is second, this is unit, this is 1 over s, and this is 1 over s squared. So these are the quantities we use to describe the motion, the circular motion. To practice, why don't we solve something? So for example, oops, I forget to save it, never mind, this is just repeating the previous lessons. So what about solving something? We have a circular motion, origin, theta equals 0, and at t equal 0 second I'm here, and my initial angular velocity is pi. And there is a pi over 2 angular acceleration. So the angular acceleration is pi over 2. At theta t equals 0, I'm at pi over 2 because the 90 degrees pi over 2. My angular acceleration, angular velocity, the initial velocity is pi 1 over s. The question, where is the body at t equal 2 seconds, for example? How to solve that? On the seminar you will solve some. Let's solve it now together. From the beta, which is pi over 2, I can calculate the omega, which is omega t equals 0 plus 0 to t, the beta, which is pi over 2, which is, this part is pi, and the second plus pi over 2 times t. Pi over 2 times t. So this is the angular velocity, how it depends on time, and what is theta t? Theta t is theta t equals 0 plus from 0 to t the angular velocity, which is pi plus pi over 2t. Theta t equals 0 is pi over 2, and this part will be pi times t plus the pi over 2t, the primitive function is pi over 4t square. So I prefer to use the order by the decreasing power of the t, so it's pi over 2t square plus pi t plus pi over 2. So this is how the angular displacement depends on time. The answer for the question, why is the body at 2 seconds, is pi over 4 times 2 square plus pi times 2 plus pi over 2. This is 4, so pi, 2 pi, pi over 2 is 3 pi plus pi over 2. But you know, it's better to write how many full rotations. So this is 1 times 2 pi, which is 1 full rotation, plus 3 pi over 2, which means the body after 1 full rotation is here at t equal 2 seconds. Alright, so it's not that easy, but also not that hard to solve that. And also the other way, when I give you the theta t, you can calculate the omega t, and then the beta, that's the easier way. Alright, so this is the kinematics of the circular motion, but a bit more interesting is the dynamics when we start to talk about energy, work, especially what is the kinetic energy of a rotating body. Alright, so let's start with the not specified body. It's a body. This is the axis of the rotation. So the body moves, let's say in this case, with the omega angular velocity. We know the kinetic energy is 1 over 2 mv square. So let's calculate the kinetic energy of this small part of the body. We know the v equal omega times r. So this body will have a speed. So let's say this is the, with the index I, the kinetic energy of the small part of this body with the index I is nothing else than 1 over 2, the mass of this part and the velocity, which is Vi equal omega times the radius of the distance from the axis of the rotation of this small part of the body. So it's omega square Ri square. Let's say this is 1 over 2 mi Ri square omega square. So as for translation, we don't have to worry about the shape of the body. It's only the mass we have to use, but at the circular motion, it's not that easy, because if you want to calculate the kinetic energy of the full body, you should simply add the kinetic energy of these parts, which is 1 over 2 mi/ri square omega square, and this is the moments of inertia. And if we can calculate it, the kinetic energy of the full body is as simple as the kinetic energy for translation, 1 over 2 times moments of inertia and the angular velocity. You can imagine that this moment of inertia not only depend on the mass of the body, but on the shape of the body. How can the math can help us? So let's say we divide the full body into small infinitesimal parts. Yes, this is the same. And this moment of inertia, which is some mi/ri square, is nothing else if the small box goes to the infinitesimal small delta v. Moment of inertia is the mass is rho times delta v, so it's rho times r square dv. Last time I mentioned this is not an easy integral, because you have to integral over a three-dimensional body, and even especially when the rho is not a homogeneous density, if there are any inhomogeneity, it's hard to calculate it. Let's look at this example with the thin ring. In some case, when, for example, the radius of the ring is much larger than this distance, you can simplify it, because let's say the small part of this body or this body or this body, if these are much larger than d, you can simplify that these distances are all r, distances from the rotation axis, just r. That means, just a minute. Alright, so in this case, this rho delta V is the so-called the mass of this body, and of course the rho is a constant times r square, and since this r doesn't depend where you are, this r square can come before the integral, and if you integrate over volume the infinitesimal masses, this is nothing else, just the full mass of the body. So this is m times r squared. So solving for simplified example is not that bad. For giving a common formula for any inhomogeneous body is not that easy, but for that we also use computer program to calculate the moments of inertia. As we calculated for this three thin ring, you can believe me, it's also possible to calculate it for mathematical objects. For example, if you have the more common we use, this is a cylinder that rotates along this axis, and if this is r, this is mass, and this is the length. Let's use for h or capital L. We can say the moment of inertia is nothing else, just 1 over 2 m r squared. So the full cylinder, the moment of inertia for this cylinder is pretty simple. For the solid, it's 2 over 5. So we mainly will change only this constant factor before the mr squared. So what does it mean? If you have, for example, a cylinder with a 1 kilogram, and look at it, so it does not depend on the length, and if the radius is 0.1 meter, what is the moment of inertia? This is 1 over 2 1 times 0.1 square, so this is 10 to minus 2, this is 0.5, this is 5 times 10 to minus 3. What is the unit? So this is kilogram, this is meter square, this is kilogram meter square. Let's suppose we rotate this body with the omega angular velocity. What is the kinetic energy of this cylinder? 1 over 2. That's from the formula of the kinetic energy. Then we should write the moments of inertia and the omega square. Let's say omega is, let's use 5 1 over s. 5 1 over s. You can imagine. Oh, somebody can't see the lecture. I will send it to you. I mean, the PDF itself, you mean? Just a minute. Anybody, so can you see the lecture which is on the right of the YouTube movie? Both. Oh, that's bad. Anybody else? Can you see the PDF in the YouTube? So not my smart table, but the PDF on your right. Do you see it? Alright, wait, let's do step by step. I sent you a link. This one. If you are new, this is a YouTube channel. If you start it, you can see this lecture 8. Alright. Alright, that's solved. Where I am. Alright, so back to my table. So omega is 5 1 over s. What's that? So phi 1 over s is more or less 1.5 times pi. That means if this is a constant angular velocity, that body takes 0.75 full rotation in every second. So not that fast, but of course not that slow. What is the kinetic energy of this body? This is 1 over 2 times 5 times 10 to minus 3 times 5 square, which is again, this is 0.5 times 5 times 10 to minus 3 times 5 times 5. So many 5. So this is 5 times 10 to minus 1 times 5 times 10 to minus 3 times 2.5 10 to 1. 5, 5, 2.5, 10 to minus 1, 10 to minus 3, 10 to 1. So this is 25, 50, 62.5 times 10 to minus 3. I move here, so 6.25 times 10 to minus 2. And this is energy, so the unit will be joule. So if we know how to calculate the moment of inertia, and if we see a constant angular velocity, it's pretty easy to calculate the kinetic energy of the body. Let's calculate another example. For example, we have a ball, not an empty ball like basketball ball, but a full ball, full sphere. And what if you rotate it with pretty fast, so like the basketball player can rotate the basketball. That's, let's say, 3 or 4 rotations per second, which is at least 10. Omega equals 12 1 over s. This is a ball with, let's say, half kilogram, so density is not that large, and the r equals 0.1, so this is a small ball. The fluid diameter is 20 centimeter. What is the energy, the kinetic energy of this ball? So this is 1 over 2 the ball moment of inertia times omega square, 1 over 2 over 5 times m times r square times omega square. So it's 1 over 2 over 5, 0.5 times 0.1 square times 10 square. So fortunately these are 1, so the rest is 1 over 5, 1 over 0.5, 0.4, 0.5, 5 times 4 times 5 is 100. It's 100 times 10 to minus 3, so that will be 0.1 joule. So if you imagine a motion, if it's a light ball and not that big, small one, even it's rotate like 3-4 rotations per second, its kinetic energy is pretty small. So compare with the translational kinetic energy when this ball moves like, let's say, 10 meters per second, but that also won't be that large. What is the translational kinetic energy? 1 over 2 mv square, this is 1 over 2, the mass is the same, 0.5 times 10 square, so it's 0.5 times 0.5 times 10 square, this is 0.25, this is 100, this is 25 joule. So sometimes it can be surprising, but if you only use the formula, usually for the same dynamics, so the same angular velocity, if you compare it with the normal velocity, of course these are not the same things, not an apple-apple comparison, you will get, because of the moments of inertia for small bodies, because this r square, you will get a smaller nominal value for the kinetic energy. Alright, now let's see how can we change this is the torque. How can we change this kinetic energy? How can we speed up a body, a rotating body? This torque is technically similar to the force in translation. So the torque in the translation, the force that divided with the mass will cause the acceleration. In the rotation, this torque, by dividing the moments of inertia, will cause the angular acceleration. So by definition, this torque is the vectorial multiplication of radius or position and the force. So look at this example. So here we have the axis of the rotation, here you have this wrench, and if you, with the force like this, you try to move the screw, not only the force that makes sense, but also the radius, or more simple to calculate with this perpendicular distance from the axis of the rotation and the line of the force, the line of the action. So for example, here we have a rotating body with some omega, with some angular velocity. If we want to speed it up, that will cause some angular acceleration. On this plot it's alpha, we sometimes use beta. And the equation with that you can calculate what this force will cause on this rotating body, what will be the angular acceleration. You should use this equation, which said the torque is equal to moment of inertia times angular acceleration. So what we learned in the Newton axiom, F equal m times a, and these are of course also vector. The torque will be equal to moments of inertia times angular acceleration. Of course, if there are more forces, like I forces, will create the net force, which will be equal to ma. If we have more torque, you can calculate the net, and that will create the angular acceleration. Let's see some example, because it's not that bad to calculate with. Let's stay here. So for example, if I have a rotating cylinder around this axis, we have some t equals 0 omega. Let's say this is 2 pi 1 over s. That means 1 full rotation in every second. And let's say we have a force that goes into the surface of the table. So let's use another perspective. So if you look at this cylinder from here, so this is no ice. This is how it rotates, and there will be a force like this. So this is the force, this is the force. And if the force is perpendicular, this d is the line of action, is nothing else, just the radius. So this is the radius, which is d. Let's say the force is 10 Newton, so the magnitude of the force, the radius or the perpendicular distance from the axis of rotation and the line of action is 0.5 meter. So it's more or less a small wheel of a bicycle. So this tau equal r cross force, but since they are perpendicular, this will be nothing else, just r times f, which is 5, and the Newton meter is the unit for the torque. How will it accelerate this body? If this body is 1 kilogram and we know the radius is 0.5, the moment of inertia for the cylinder is 1 over 1 times 0.5 square. 0.5 is 0.5 square, so 0.25, 0.125 kilogram meter square. So what is the equation to calculate the angular acceleration? So the torque is moments of inertia times alpha. This is 5. This is 0.125 times alpha. Let's use the nominal values, not the vectors. If you divide 0.25, let's say multiply with 8, So the 40 is the alpha, which is a pretty fast, pretty extensive angular acceleration, since that means you will increase the angular velocity close to, let's say, 12 full rotation per second in every minute. Alright, we will solve more examples on seminars. By the end of this semester, we will solve some example for pure rolling motion. For that, you have to remember how to calculate with the friction, and we will solve these kind of examples. So pure rolling is nothing else, just moving a cylinder on a flat surface, but there is friction, and we move this body by a force that goes through the axis of the rotation. This is a pretty simple, but since there are 3 equations and 3 unknown, you have to practice not to screw up the calculation. And if you remember, the friction is also not that easy, because friction can be or can't be large enough for static friction, and sometimes we have to change the equation for kinetic friction, so that needs some concentration from the students to solve these kind of examples. The pure rolling is the case when we can talk about static friction, and there is a non-pure rolling when the friction is not enough to fulfill the conditions for... Sorry. Thanks for your patient time back. So these will be the example you should solve whether in the test 2 or this will be one example for the exam. So what you have to learn from this lesson is moments of inertia and calculate the rotational kinetic energy of a body and how can we change this energy. You know, the path integral of the force is the work is the energy transfer. In the most simple case, when this body moves on a frictionless flat surface, is the kinetic energy. For rotation, we don't only use the force, but also this perpendicular distance between the axis of the rotation and line of action. From that we can calculate the torque, and the torque will be the action that will change the energy. That's all. So since I have an extra lesson from 9, I stop here and let's meet on the seminars and you can ask questions then, because I have to change the course right now. So thanks for your patience. I will send you the PDF also, but I need some time to reorganize my presentations for these online courses. Thank you very much and bye.